In this short lesson, we're going to use Dalton's law of partial pressures. Remember that Dalton's law states that the total pressure of a gas mixture, the mixture of gases, is the sum of the individual pressures, what we call the partial pressures, of all the gases that are present in the mixture. Now, looking at the screen here, you'll notice some information about pressure, also information about oxygen gas and CO2, carbon dioxide. What we're going to do in this short lesson is, using this data, we're going to determine the partial pressure of both oxygen and carbon dioxide in this classroom. To do that, you'll notice we have a gas pressure sensor, basically a barometer measuring total atmospheric pressure. Now remember that our atmosphere is a mixture of gases, mostly nitrogen and oxygen, some carbon dioxide, and then an assortment of other gases, including argon and other noble gases, water vapor, things like that. Now, we also have connected to the computer two gas sensors. We have a carbon dioxide probe and an oxygen probe. And those are specifically measuring the concentration of oxygen and carbon dioxide in the atmosphere. And those are reported on the screen, the data. So for the oxygen gas, our concentration in the atmosphere right now in this room is about 19.6%. I'm sorry, 19.16%. We're fluctuating around 0.16. For CO2, the concentration is being measured in parts per million, that's ppm, because CO2 is actually at a very low concentration in our atmosphere. It doesn't take much CO2 to have a significant effect on the atmosphere, but it is at a very low concentration. So parts per million of every 1 million parts of air, that's how many parts are carbon dioxide. And that's pretty steady right now at 334 parts per million. So to do our problem then, we're going to use this information. Okay, so continuing here, we want to figure out the partial pressure of oxygen and carbon dioxide in the Earth's atmosphere. And we're going to use this pressure. This is the atmospheric pressure right now that we measured. It was about this, as you saw. So we'll go with 101.21 kPa, kilopascals. The oxygen percentage, we said we're going to go with 19.16 because we were fluctuating between 0.15 and 0.17 most of the time. And then for CO2, we'll go with 334 parts per million. Again, that's a very low concentration. Out of every 1 million parts of air, 334 of those are carbon dioxide. Not very much, but still significant. Now, what we're going to use here is something called the molar ratio, okay? Which is a fancy way of saying, what are the ingredients of our mixture of air? In this case, what are the ingredients of the atmosphere by how many parts they make up of the atmosphere. That's the molar ratio. Sorry, let me spell that correctly. Molar ratio. Now, what we can do with our oxygen percentage and our CO2 parts per million, we can make a simple ratio. For the oxygen gas, O2, we're simply going to take this percentage and put it over 100. Because, the percentage is always out of 100. So our molar ratio for the oxygen is 19.16 over 100. For CO2, carbon dioxide, so the ratio for carbon dioxide, we can use our parts per million, and we'll put this number over 1 million parts, which is the total parts of air. So for CO2, our molar ratio will be 334 over 1 million. Now, to get the partial pressure of each gas, what we're going to do simply is multiply the total pressure by the molar ratio, by the fraction for each gas. So the pressure of oxygen right now in the room, PO2, would be equal to 19.16 over 100, that fraction, times 101.21 kPa. When you do the math, that comes out to 19.39 kPa. And again, what that tells us is that of this 101 kilopascals, a little over 19 of them are being caused by the oxygen specifically in the atmosphere. This is the partial pressure of oxygen right now in Earth's atmosphere. For the CO2, we'll do the same thing. 334 over 1 million, and we'll multiply that by 101.21. When we do that, we get a small number, 0.03380 kilopascals. That is a very small number, but remember that carbon dioxide is at a very low concentration in our atmosphere. So carbon dioxide's partial pressure, 0.03380 kPa. That much of our atmosphere's pressure is being caused directly by carbon dioxide. Now again, you might wonder, well, wait a minute, shouldn't these two pressures add up to 101.21 kPa? And you might think that. But remember, our Earth's atmosphere is mostly nitrogen, N2. Neither of our probes takes into account nitrogen. We don't have a probe to measure that. So that's why these two don't add up to 101. The other 80 or so kilopascals of pressure in the atmosphere, most of those are being caused by nitrogen. So Dalton's law, partial pressures added together equal the total pressure of a gas mixture. And in this example, we can use the molar ratio to figure out the partial pressure of specific gases. Okay?